And yeah. All right, so the population density, you have basically, you can almost imagine this kind of like a field, a few different habitats and the different ways that the organisms are spread out. When we look at different types, so we have the very uniform, evenly distributed to sort of like a cluster environment, which is what 3B is talking about. So this one, fill in the table below, counting the number of individuals in each habitat. So like habitat number 1 was amassed with a whole bunch of dots, and they all had the same square area. So it was almost like a pasture, right? So then we get into population density. So for this first one, you have a population density of 7.75 people per kilometer, to where it was really low in number 2. I'm going to switch back really quick at 1 person per kilometer, since there's 4 kilometers squared and 4 individuals, and so on. So it's just a simple population density calculation. How many people per area? When we start splitting the habitats up and creating them or splitting them in half, it starts giving up the amount of population density that they have. The biggest change is in area number 4. So in habitat 4, when it's kind of in its clusters and it's not so evenly distributed, let's see. Is somebody waiting? Oh. Leland, this is in your note packet.
How come you weren't?
You were in the old one that wasn't working. Everything that had gotten deleted back in around Thanksgiving break came back over winter break, and you were in that old one. And KK, I'll get to that in a second. So we've got our even distribution, even though it's split in half, to where habitat 4, because of the clusters, and there was more clusters on one side, your density changes. And so you could even think of this almost as like a city and a suburb as far as people go, not just animals. To where this might be, these bottom ones might be more like as you're heading out towards Falcon. All right. So that's kind of what this table is reaching out at, is how the population density changes when you spread out. Hold on. There was one more thing I wanted to cover. Assuming the population size stays constant, propose at least 2 factors that might cause population to shift from a low density to a high density habitat. So what's going to cause them to move is like a loss of a food source or some sort of change in environment. That could be one of those natural disasters when we're talking resilient versus resistant, and things like that. What did the clumped one say again? I don't know that it said anything, but number 4 was our clumped. All right, so like I said, I gave you guys all the answers in your PowerPoint on total accident. I guess that's what happens when you work over winter break. Sorry, although you guys probably aren't upset about that. Is there any questions on just population density? And then I'll go back to that birth and death increase for you, KK.
Please don't tell me we have a note packet that we're filling out right now.
Yep.
Shaking my head.
Should I put that in number 2?
He really said that.
So for the 2 bullet points in this part, what do we put down?
What part?
For the two bullet points under decreased births and decreased deaths.
So births and immigration, and the decrease is deaths and immigration.
Okay, thank you.
You're welcome. All right. Let's see. Okay. So are you guys good on this first PowerPoint? I know we went over most of it last week.
Yep.
Okay. Javea, trying to find a way to put it into your packet as close as you can. The tables are going to be really difficult. I'm not going to be upset if I don't see like the tables filled out. But you can draw it in, or you can do the insert text box. I need to find a way to convert that to Word so you can type in it.
There is a way, but I forgot it.
I mean, because I only have the file as an image, not even a PDF, and I can convert PDFs really easily, so there is that. Alex, do I need to throw a note packet into the parking lot?
Yes, please.
Okay. All right. Okay, so again, going into kind of populations and things like that, we're going to start talking about what's called K and R selected species and survivorship curve. So like how many people stay alive for how long?
Wait, Miss, I have a question.
Yeah,
When you're in school, are you in school right now?
yeah,
Is Papa there too?
yeah, she's here.
Do you mind giving Papa the paper? I can get it from her from practice today.
Oh yeah, absolutely.
Thank you.
Yeah, you're welcome. Hold on, I'm just writing it down so I don't forget. All right, so life history strategies. This is part 2 of your notes. Life history is just the series of events from birth through reproduction to death. When we talk about the R and K selected species, it's really just through reproduction. And then the survivorship is a little bit more about death. I'm going to get all of these up first. All right, so when we talk about life history strategies, there's a few things that tend to influence the growth rate of a population. The first thing is the age of first reproduction. So how quickly are they able to reproduce? Number 2 is the number of offspring. Is it just 1 or 2, like humans or horses or anything like that, that don't have very many at a single time, versus like you can see in the picture, a turtle having a whole bunch of eggs, right? So total number of offspring. Number 3, the amount of parental care given to an offspring. Unfortunately, this is like one of my favorite labs that we won't get to do because yay, COVID, where you guys have to take care of bubbles. But the amount of parental care can be very taxing on a ecological or on a population's community. So that is a big thing too. And then the energy cost of reproduction. So how much of the female's energy and even the males when it comes to keeping the female happy and healthy and able to reproduce. While I'm waiting for you guys to finish writing this down, other than Alex and Ashley, is there anyone in here who would like me to get them a paper version of the note packet? Turtle eggs, I think it depends on the species of turtle. The ones, if I remember, this is a picture of the ones that lay eggs in Costa Rica. And they're roughly like, I don't want to say like golf ball sized. All right.
Ms. Peterson, can you go back one
Yeah.
slide?
Yeah. Maybe. There we go. The blank is just life history, series of events. Definitely not like grade A chicken eggs. The reptiles tend to have softer, like squishier eggs. So it's not like chicken eggs that you would think of, or bird eggs in general, that have that hard shell. All right, are you guys good if I move on?
Yeah.
Oops. All right. There's not a spot for you to write this, I don't think. So, life strategies, which really all that means is just how animals live their lives or organisms live their lives. They're shaped by evolution and natural selection. And every population has a life history adapted to its own environment. So, like thinking of the turtles on the previous page, or even the ducklings on this one, in completely different environments, you're going to have slightly different way of how they live and reproduce, even if they're a similar species. So for our selected species, when it comes to energy into reproduction, not necessarily survival. So these are the species that have typically like a whole lot of babies, and then sometimes maybe die off. So not a whole lot goes into surviving. It's just purely about reproduction. They're very poor competitors, so like they can get taken out really quickly. They're typically what's called an opportunist, which takes advantage of a favorable environment. And so it can, that tends to be when you see them populate a little bit out of control. When favorable conditions are gone, you tend to get a population crash. So they might be like breeding exponentially, a whole bunch of them, something about that environment changes and boom, they're gone. And so with that, you tend to get really irregular or unstable cycles. And I think, what was it, I think it was last unit, we looked at like the hare and fox or something population graphs where they just kind of almost look like something you'd see nice and pretty in a math class. Our selected species aren't necessarily so pretty like that. Why are your fingers? You're the second one I've heard complain about that in less than a week. All right, I'm gonna move on soon. All right. Hopefully you guys are good. If not, you know to yell at me. All right, some characteristics of an R-selected species. Oops, sorry. Small body. So I always think of a really stereotypical example is fruit flies. They like, I swear to God, it's not real, I'm exaggerating, make millions of babies and then they die 48 hours. right after they're born, or 72. So I always think of bugs when I think of R-selected. They reproduce when they're young, have a ton of offspring, and a very low survival rate of those offspring. So when you see organisms that tend to have a ton of offspring, it's generally because of a low survival rate. And we'll even talk later with humans. It used to be really common to have between 10 and 20 kids. It's not that common anymore, but it was because of a low survival rate. Little to no parental care, so you don't have like mama and daddy fruit flies taking care of their kids for years to come. You have an exponential growth. I always think of mosquitoes here. The second there's a body of water around, they exponentially grow. And then unpredictable environments controlled by what's called density independent factors. So those are things in the environment that have nothing to do with how many organisms are there or not. And then we'll talk about the 3 different types of survivorship curves in a minute, but it's typically a type 3 survivorship curve. So here's some examples. Bacteria, algae, which I would like you guys to grow this year, but we'll see how that goes. Most annual plants, not perennials. Dandelions, insects, cockroaches, rodents, oysters, believe it or not, are part of this. That one actually kind of shocked me, but it kind of makes sense. You don't have to write down all of these, but get a few down that help you remember. All right. So the second one is case-selected species. They put most of their energy into survival as opposed to the reproduction. There's a high amount of parental care, like you guys getting taken care of, right? And then versus like a fruit fly. They're very good competitors, so we can adjust and we can outcompete other species, which is why there's over 7 billion of us. And then we thrive in ecosystems with fairly consistent environmental conditions. We don't typically like a whole lot of changes. And then we tend case-selected species tend to remain close to carrying capacity over long periods of time. You're going to see a little bit of wobble with population, but they kind of like max out and then just kind of stay right around that population. Humans being the exception. We've pretty much passed a natural carrying capacity already. Some characteristics of case-selected, some of your bigger organisms, they tend to have or reproduce later in their lifetimes, not right off the bat, fewer offspring, and most of them survive. Like I said earlier, there's the higher parental care, the predictable environments, and they are controlled by density dependent factors. And like we'll go through some of those later on. But those are the factors in the environment that are related to how many organisms there is in a given area. And then a type 1 survivorship curve, which we'll see in just a moment. Yes, Javea, I'll go back. There you go. All right. All right, am I good to move on from this slide? Hopefully.
Give me 1 more minute.
Okay.
Yeah, 1 more minute.
All right. All right. So some examples, again, you can just write down a couple. Humans, large trees, so like your oaks, your firs, your pines. Polar bears are one, elephants, most mammals and birds, like the pretty orca whales over here. They don't have a whole lot of babies and they hold on to them for a pretty long time, considering their lifespan. So. All right. So when I said there was a few different survivorship curves, this is what I'm talking about. So relative age, so like a lifespan for a human, 80 years, but maybe a lifespan for a bird might only be 10. So it's kind of like a percentage of the relative age or lifespan.
Do you
And then,
like?
what's up?
I said, do we draw this one?
Yeah, you don't have to draw like the egg, the duckling, the bird, or whatever baby adult, but at least get like the shapes of the curves down. and type 1, type 2, type 3. This is something I could almost guarantee that you'll see on the AP exam. So the bottom is the age, relative age, and then the left side is the number of survivors in a logarithmic scale. For those of you that don't know what a logarithmic scale is, it is something that goes by tens. So you could think of exponential. If you've done any math with earthquakes, like the Richter scale, so like a 5.0 earthquake versus a 5.1, that's 10 times stronger than a 5. So the Richter scale is also done off a logarithmic scale. So that's why the scale looks like it's uneven when it's really not. It's just to make the graph more usable. The other chat, Jesus, is coming from the previous Teams classroom that I had before everything got deleted over Thanksgiving break and then magically came back. So draw those 3 curves in. Type 1, type 2, type 3. Yeah, actually, I'll blow it back. I was just going to switch to PowerPoints, but if you want to screenshot it, the only thing is my stupid start bar won't go away. It does sometimes, and it won't other times. You can screenshot it and put it in there. That's totally fine. Probably smarter to do that, actually. I always forget. All right, I'm going to switch over to the other PowerPoint really quick. So this is section 3. Like I said, I'm sorry, but we're just trying to cram through some of this today. Population growth and resource availability. So we've talked a little bit about carrying capacity already, kind of when the organisms or community population reaches kind of a maximum based on those limiting factors. And we've discussed the limiting factors before as like the amount of light, how much water is available, the amount of space, number of competition or other organisms, and also predation as well. So all different types of limiting factors, and based on the species, you could have other ones as well. Like we talked a lot about nitrogen being a limiting factor for plants.
Why? Okay, sorry, off topic. If I'm only missing 4 elective credits, why would you put me in 5 elective classes for this year when I'm behind on other credits? Upsetting.
That is a wonderful question, Alex. I wish I had a politically correct answer for you.
So I just emailed my counselor and I'm gonna figure out things.
Yeah.
That's why I'm not really caring about your class right now. Sorry.
Did you become Australian all of a sudden? All right. Oh, and I forgot there's one more disease. I forget that my start bar cuts things off. Like we're kind of dealing with right now. All right. So intrinsic rate of increase is often referred to as a lowercase r. That is a rate of population growth with unlimited resources. So that's like having zero limiting factors.
Do we draw this part?
No, you don't have to draw this one.
All right.
It just intrinsic rate of increase is what goes in your packet. So no limiting factors, unlimited resources, all the amount of food you want, all the amount of shelter, water, all of it. All the baby mamas ready to go. Oops, sorry. There we go. 4 characteristics of rapidly growing populations. So we kind of talked about the R-selected species and rodents being one of them. Their timing of reproduction is very early in life.
That's a lot of babies for a mouse.
It is. That is actually a lot for a mouse or a rat.
I estimate 50.
I don't know about 50.
Well, from where the picture is taken, it looks bottomless.
That's true. I can count 17 in there. Still a high number. All right. Number 2 on there, the amount of time between generations. Freaking stink bugs. I hate these things. Short generational time. Generation like kids, parents, grandparents, great-grandparents. My dog would eat these when I lived out in Maryland and would puke back up. It like obviously didn't work well with her system, and she loves chasing bugs, so it was.
One of ours likes to chase grasshoppers.
Oh yeah, that's weird. I've never heard of anyone eating stink bugs. Oh,
Did you know that grasshoppers taste like shrimp?
I've eaten grasshoppers before, and that is, I don't know. They just taste.
I don't know
crap.
if I read that somewhere.
Yeah, people like bugs in a lot of cultures, like, and not probably like almost everywhere but America, really are a thing. Like people eat them, and they're a very high source of protein, so they're typically really healthy.
Chocolate-covered scorpions.
Right? Yep. I had a teacher in high school or junior high, I think, that used to bring in all sorts of weird stuff. Another characteristic of speedy populations is the length of their reproductive lives, so that they can have babies more than like once or twice. So they can get as many reproduction cycles in as possible.
The long reproducers. Is it true that the longest reproducers are asexual reproducers?
I need you to follow directions. If I tell you to stop doing it, you will stop doing it.
I would say probably, just because that organism, the moment it dies, I mean, it can reproduce pretty much until the moment it dies. I would not be surprised at that. It makes sense. All right.
Where's the box down here?
What's that?
Oh, on our packets it says number of offspring, and then right below it says this is.
We're gonna get there.
Okay.
All right. So when we talk about the number of offspring, because you know science, we have to have 4,000 fancy terms for everything. It's called fecundity. And so that's that little bracket in that last box. So many offspring is high fecundity, low offspring would be low fecundity. It's a weird word. I'll be honest, I probably won't use it a whole lot, but it is something you'll see in like questions and things like that.
What I've noticed, every time that we have to use scientific words in like a Word document or something, they come up as wrongly spelled.
Especially if it's one of my jobs, I used to have to identify like species, and I could only use their Latin names. It was like whole documents of just red squiggly underline. Really annoying.
Yeah, they do that with all the other languages too.
Yep. So carrying capacity often gets shown as K, and here's where biologists are freaking annoying, and I hate them. This has nothing to do with K-selected species. Just like the intrinsic rate, lowercase r, has like not necessarily anything to do with R-selected species. We have 26 letters in the alphabet. I don't know why they don't use them. So carrying capacity you'll often hear as K graphs or whatever. It is determined by biotic potential. And what biotic potential means is the maximum reproductive rate of a population in ideal conditions. So living potential, basically, is kind of another way to put it. It's capacity for growth. Another thing is environmental resistance. We talked about the resistance versus resilience and the factors that can limit the growth. So resistance to those changes. And then as populations reach the carrying capacity, growth rate decreases because resources become more scarce, along with other things. But if you think of like going back to our little 4 kilometer squared POGL, 3.1, and as your population grows and you only have that amount of space, eventually you're going to run out of space. You're going to run out of food, or you're going to be competing for food. And then you're going to end up having to compete for water or mates or anything else like that too. And if you're a population like, the king penguins, where it's a mate for life, then yeah, you're really going to be screwed. So it's not like some male part of the species can come in behind another one and take care of things to reproduce. So a few different things that change. The emperor penguin, thank you. It was royal somewhere. Emperor. That's why I'm still drinking coffee. I'm on like my 3rd cup here at school. So what happens to mortality? Do you think mortality increases or decreases as you approach a carrying capacity?
Can you repeat the question again?
Yeah. What happens to mortality or death rates as you approach carrying capacity?
Decrease.
I would agree with you guys. It would be a little bit more of a decrease. Once you hit the carrying capacity, then you'll see an increase. But up into you get to that point, it's going to be a decrease in mortality. All right. With fecundity or the amount of offspring, what do you think happens?
Increase, maybe? No, probably decrease.
If I say both answers, one of them is going to be right. All right. So this is where it really kind of depends on the species, and try not to think of humans, because we are kind of the exception to the rule. So with fecundity, you are still up through hitting carrying capacity, you're still going to have lots of babies. And then once you hit it, like humans did, we've kind of tapered off, but that was not due to environmental impacts or resources or anything like that. But chances are the mortality rate of your offspring is then going to increase. So you're going to have an increase of babies continually, but
So this would be increased.
yeah, but their mortality will increase.
Okay, what? You confused me.
So
As the population reaches carrying capacity, growth rate decreases.
your
Mortality rate.
your growth rate decreases. You could still have the same amount. I guess you could put decrease. You still have the same amount of babies, but the babies are gonna die, right? Because there's not going to be enough resources. They're going to be competing, kind of like the polar bears are right now.
Okay.
So
the placenty would increase, mortality would decrease, or vice versa.
Flip it.
Yeah. Okay.
Yeah. Overall, like if you were to average it out, it would be a decrease. But you're still going to have the same amount of babies that increases your population, but many of the babies are going to die for lack of resources. All right. So there's a couple different curves, and I think Leland's got the right idea to probably screenshot and just put it in there. Your J curve is your exponential growth. This is one of your types of curves. This is your unrestricted, a lack of limiting factors. This does not last indefinitely in real life situations. One example that we could see with an exponential growth population is going to be any sort of invasive species. So something comes in, and then just, if any of you have ever seen kudzu, which is not here in Colorado, but it grows, it's a plant that grows like up to 2 feet per day. And it completely chokes out entire ecosystems, and it's kind of cool to watch. Not good, obviously, but it's interesting. It is an exponential growing invasive species, but eventually it's going to have to taper off. It's going to hit that carrying capacity. It's going to hit some sort of limiting resource, and then that graph will start to taper out. You can draw in the graph, KK, or you can screenshot it and substitute and put that in instead, which is probably the easier thing to do. All right. The next graph, this is in my way. Hold on. The next graph is called the S curve for sigmoid. It's just the S curve. And it's called logistical growth. And that's when the carrying capacity is introduced, those limiting resources are introduced. You do have a little bit of exponential growth down here at the initial start of the species, and then eventually that rate starts to slow down. That is when those limiting factors start taking effect. Ooh, got like hiccups. All right. Next slide. Oh, I just wanted to show this really quick. When you have your exponent, like that initial exponential growth, when that species comes in, the limiting factors tend to take place and it slows down, and you overshoot your carrying capacity. So when you see that big spike above that carrying capacity line, that's the initial, like, oh crap, we're pulling the e-brake on our population moment. That's when you get a very, very quick die off, and they kind of starts to oscillate or die back or die off, and it starts to oscillate just kind of around that carrying capacity based on those limiting factors and their availability, based off any kind of natural disaster events, anything that they might that might affect their population.
So like kind of when they release the wolves in Yellowstone.
Ideally, this is what it would follow, but there's obviously a lot of external factors that will affect that. But yes. All right, your exponential growth equation is n sub t equals, and not e to the rt, because we love letters when it comes to math. I know everybody does. Oh, and I'm going to tell you what those all mean in a second, but that is your equation. And the rt is exponents, like something squared type thing. And we'll get through all the meanings, and then we'll probably pause.
Where do we write this equation at? In the box that says equation?
Yep.
Or the one under it that has the NO?
That one I'm going to give you what each of these things mean, like initial, final, rates, time, blah, blah, blah.
Okay. I'm gonna have to write this because I can't type it.
Okay.
Well, see, I can see the whatchamacallit moving, but so I presume that the lettering's white, but I go and change it and it stays white.
I have no idea. All right, I'm moving on. All right, so we're going to go through what each of these means really quick before you go. N sub 0 or N naught, you'll hear it either way, is the initial population size. R is a rate of growth, which you generally get given. E is a constant. We can go with the history of that if you want, but it's 2.7. T is the amount of time, whether it's years, months, weeks, hours, whatever. And then N sub T is final, your final population size. Random note, this is how you calculate compound interest on your credit cards and savings accounts. Same equation. So once you've got those down, we'll hopefully finish up some stuff next time. I'm going to start you guys on a cemetery lab on Thursday, and you do have a couple DOLs to do. You can at least get through like 3.1 and 3.2, I'm pretty sure. And yeah, if you guys don't have any questions, I will. Oh, I do have one other thing to say. I forgot, those of you that are doing the sweatshirts and the designs and stuff for that, after advisory today, I've set up a calendar invite and sent you guys last week. A couple people responded, but just so you guys know. Other than that, I will see you guys in a couple days.
Okay. Thank you, Miss.
You're welcome, Leland.
Bye, everybody. See you on Thursday.
Hi, Jackie. Asia, we have another meeting today. Yes, we just have one in general. That way we can finalize some stuff. Hopefully. Go back to the factors in our selection examples. Oh, I think that was in my other, is it this one? Yeah. Let me open up that PowerPoint real quick. Yeah, what's up?
We are supposed to leave, right?
Yes.
Okay. Bye.
Characteristics. Jesus, is that what you needed? Bye, KK. All right. There you go.